Okay, so this lecture covers the basic kinematics, if you will, of alternating current. Make sure that you take a look at the 2 demonstration videos prior to taking a look at this lecture. Okay, so here's how we mathematically describe alternating current. Okay, first of all, let me draw up the following circuit. Okay, right here is the generator symbol. Okay, we write it as a sine curve for reasons as you'll see in just a few minutes. Okay, and then right here is a resistor with a resistance R. And all that we're going to have present here within this circuit is the generator itself and the resistor of resistance R. Okay? Okay, now alternating current basically follows the following graph. Okay, what we're going to do is we're going to plot here the current as a function of time, and when we do, it traces out a sine curve like so. Okay, one complete oscillation, this right here then corresponds to the period of the oscillation. And then here and here is basically what is referred to as the peak current, a value of I naught in one direction and negative in the other. And then the function itself is described in the following way. Okay, omega, the angular frequency, is equal to 2 pi times the frequency f, and the frequency f as a standard throughout the entire world is 60 hertz. Okay, now it's initially a little bit difficult to picture exactly what is happening with alternating current. Here's what's not happening. The current, every period, is not oscillating from here to here within the circuit and then going back again like so. Instead, each section of the wire, if you can somehow look at the electrons themselves, what you would see is essentially along each section of the wire, the electrons then oscillating in place like so with a relatively small amplitude. It's as if each section of the wire is like a pinball machine that's tilting up and down like this 60 times per second, and then therefore over a very small distance, the actual electrons are oscillating back and forth like this. That's basically what's happening here along each section of the wire, okay? Okay, now what I'm going to do here mathematically is calculate the average amount of current over an entire period. In order to do this, what we have to do is we have to integrate this function here and then divide it by a period. That will be the average amount. Okay, watch what happens when I do. All right, the average amount of current here is going to be equal to, first of all, 1 over the period itself. We're dividing by time. And then what we have to do is add up the function over a complete time interval, over a full period, capital T. Like so, okay? Easy integral to perform. Let's do a little bit of U substitution. Like so. Like that. And then let's go ahead and start to plug in and switch variables around a bit. So when I do, I start to obtain the following. Like so. And then this quantity right here, by the way, you're going to see this pop up a few times over the course of this derivation, is 2 pi divided by the period, capital T, and then multiplied by the period, capital T. So this quantity right here is 2 pi. Okay, that'll become important a little bit later on. Well, let's go ahead and integrate this out here. So the integral of sine is negative cosine. So switch the variable back. Okay, and now we're going to have the following. Let me go ahead and write here in the denominator now, 2 pi like so from a moment ago. And then I have here cosine omega times capital T again. So that's going to be the cosine of 2 pi, and then minus the cosine of 0. So I've got right here the cosine of 2 pi, which is 1, and then minus the cosine of 0, which is also equal to 1. 1 minus 1 is 0, and then therefore the average current is equal to 0. So you average the current over a complete period, you end up with 0. This seems like a paradox because after all, for example, if you look at my demonstration videos, obviously energy was being delivered by a generator, yet the average amount of current is equal to 0. So how do we account for this mathematically? Well, mathematically, basically what we do is we don't average the current. Instead, what we do is we take the current and square it, and then we average that. And then at the end of the process, we then take the square root. This pops up in a power calculation. So here's how the power calculation works. Okay, so what we're going to do is we're going to calculate the average power delivered by the generator, but as long as this circuit just consists of a generator and a wire, a resistor, This is then therefore the same thing as the average power loss within the resistor, the energy lost as heat. Okay, now go back to the direct current lectures for a few moments. Okay, from direct current, recall that P delivered was equal to I times V. And then if all that you have in the circuit, once again, is a resistor, then the P loss is equal to P delivered. And then through Ohm's law, you can write this as an I squared R, or alternatively, as a V squared over R. So what I'm going to do is this calculation right here. We'll do the voltage calculation as well a little bit later. But let's do this calculation right here. So what I'm going to do is take essentially the average of this value. And I'm just going to refer to this as PR. That's perfectly fine. But the average of I squared R is now the following. Once again, we divide by the period, and then we add up over a period I squared R, where I squared we're going to take is this right here, and then square this. So I naught squared R, and then sine squared omega t. So the process is take the value of the current, basically square it. That's essentially what I'm doing here. And at the end of the process, then we're going to take the square root. Okay? All right, so let's go ahead and perform this integration. First of all, let me pull out the constants. Like so. Okay, let's change variables. Once again, a little bit of u substitution. So, okay, rewrite. So once again, here is a 2 pi from a few minutes ago. And then we have integral of sine squared u du. Okay, the integral of sine squared is one of those strange integrals. Okay, the integral of sine squared, if you don't recall from calculus, is the following: 1/2 times u minus 1/4 times sine of 2u. Like so. So that right there is the antiderivative of sine squared. Let me just double check that in my notes. Yeah, like so. Okay, now let me go ahead and switch the variables back. Here. Okay, from before, once again, this is a 2 pi. Okay, and now I'm going to have the following: 1/2 times omega little t minus 1/4 sine of 2 times omega little t. Like so, and then we evaluate rather between 0 and capital T here. Okay. All right, so let me go ahead and plug in. R over 2 pi. Okay, and now I've got 1/2 omega times capital T minus 1/4 sine of 2 times omega capital T. Like so. And then when you plug in 0, you end up with 0 here, minus the sign of 0, which is 0, so everything here drops out. Okay, and then this here in brackets then simplifies in the following way. Right here is once again a 2 pi, and then right over here is going to be the sine of 4 pi. The sine of 4 pi is equal to 0, so the sine term drops out. This then means that this right here simplifies to become the following. Okay, so simplifying that, the average power that is lost through the resistor or equivalently delivered by the generator is now the following. I naught squared R over 2 pi, and then multiplied by 1/2 times 2 pi. Like so, 2 pi's cancel out, and then we end up with this. Like so. So compare this quantity here to this quantity here. Essentially what we did was we took I squared in this calculation and then averaged that. That's actually this guy right here. So off to the side, the average of I squared. So it's not the average of I squared, it's the average of I squared. The average of I squared is this quantity right here. Take the square root of that. When you take the square root of that, you end up with what is referred to as the root mean square. And you write that in the following way. like so. This one you have to commit to memory. It is easy to memorize, however, they will not give you this formula on the AP exam, but they do expect you to know it. So the peak value of the current divided by √2 is equal to what is referred to as the root mean square. So then therefore the average power in this calculation that we just performed is IRMS squared multiplied by the resistance R. This is basically the alternating current version of this calculation right here associated with direct current. Okay, and then what about the voltage itself? Okay, the voltage is essentially the exact same calculation, but instead of an I squared times R, it's a V squared over R. But here's ultimately how you describe that mathematically. Okay, now the voltage across the generator, same thing as the voltage across the resistor, is described in the following way. Voltage as a function of time is a peak value multiplied by, once again, sine omega t. So if we graph this out, the voltage as a function of time, it's just, once again, a sine curve like so over a full period. And then you have peak values of the voltage here and here. Okay, there is a standard VRMS in a few minutes that's equal to 120 volts as a standard in the United States. This is the voltage of what you would get out of a wall socket, for example. We'll see that in a couple of the example problems in just a few minutes. Okay, here's how this average calculation is performed. I'm just going to set it up because ultimately it's the exact same integral. So when you set up this calculation here, P bar, we're going to write this now as 1 over the time of the following integral. Basically, V squared over R. Like so. So we're doing now the alternating current version of this guy right here for direct current. Okay, it's the exact same integral as before. So then therefore, when you ultimately do perform the integration, you basically end up with this. Like so. And then right here, the V naught squared over 2, that right there is the average of V squared. So that's then written like this. Like so. And then we take the square root of that to then end up with the root mean square. So the root mean square value of the voltage, this is the 120 volts that comes out of a wall socket, for example, is equal to the peak value divided by √2. So then therefore the alternating current version of V squared over R for direct current is now this. Like so. Okay, so once again, basically what we're doing here with these integral calculations is taking either the current or the voltage, squaring that, averaging that, and then taking the square root of that at the end of the process. That's basically what we have. So then therefore, to kind of summarize here are then therefore more or less the kinematics equations, if you will, for alternating current. Okay, so the average value delivered by the generator itself, call that now P deliver. That's going to be specifically IRMS times VRMS. But then if you're talking about the loss through a resistor, then P loss is equal to IRMS squared times R, or equivalently the voltage across the resistor, VRMS squared over R, like so. So you basically end up with the exact same expressions for alternating current as you do for direct current, but we have to perform these average value calculations, okay? Okay, so now there are two problems associated with the basics here of alternating current. The first of those two problems has to do with the electric motor. So let me go ahead and read the problem here for you, and then go ahead and pause and copy down into your notes. Okay, what is the efficiency of a 0.5 horsepower electric motor that draws, as we say, 4.5 amps from a 120 volt line? So the terminology that's being used here is common in electrical engineering. The 120 volts is VRMS, and the 4.5 amps is IRMS. Okay, what is the resistance? All right, so let me erase. Go ahead and pause and copy it down. All right, so here are the values that we're given. All right, so first of all, we have 0.5 horsepower associated with electric motor. I'm going to refer to this as P motor. This is equal to 0.5 horsepower. Let me immediately convert this into watts. It's been a while since we've seen this. But 1 horsepower is equal to 746 watts. So then therefore 746 divided by 2, I can't do this in my head anymore. And that's 373 watts. Okay. Okay, and then we're given VRMS, 120 volts, and then we're given IRMS, is 4.5 amps. Think of the electric motor here, however, as two different things. So we have, first of all, the generator. Once again, there's the generator symbol. And then we have two things associated with the electric motor. Okay, there's first of all a resistor here. The electric motor heats up. There's a resistor here of resistance R. That's basically the wire within the electric motor. And then this circle symbol here is just a generic symbol that we use to describe some other circuit element. In this case, it's the rotating armature, as it's called, of an electric motor. That's what provides for us useful rotational kinetic energy to do work and so on and so forth. So this right here, if we want to think of it, is the motor itself, but the wire associated with the motor, that's the resistor R. Okay. Okay, now let's calculate P delivered with these IRMS values. This is the amount of energy per second that's being delivered by the generator. All right, so P deliver is IRMS times VRMS. Multiply the two together, so 120 times 4.5. And that comes out to be 540 watts. So notice that there is a difference between this value that's delivered by the generator and this value here associated with the rotation of the operation of the motor. The difference between the two, that's the amount of energy per second that's being lost as heat within the resistor itself. Okay? So then therefore we can calculate what is referred to as efficiency. Okay, obviously you want to make the efficiency as large as possible when doing mechanical work of some sort. Okay, so efficiency is always defined, by the way, as output divided by input, and we'll multiply that by 100 in order to convert it into a percentage. So the output in this case is the amount of energy per second associated with the operation of the motor. Okay, this is once again the rotation of the armature. That's the 373 watts. And then we divide this by what we ultimately put into this by means of the generator, that's 540. And then we multiply by 100 in order to convert this into a percentage. All right, so 373 and then divided by 540 and then multiply by 100. This comes out to be about 69%. So 69% of the energy basically per second that's being delivered by the generator actually ends up as useful for us in the operation of the motor. Okay, the difference between the two is the amount of energy lost as heat per second within the motor itself. We'll use that then to calculate the resistance of the motor. Okay, so P loss now. This right here, that's going to equal then the P delivered. And then subtract from that then, let's see, the P motor, as I'm referring to it as. Like so. And that difference is 540 minus 373. And that comes out to be 167 watts. Okay, this P loss now, 167 watts, this is then what I'm going to set equal to the following. I'm going to write it as IRMS squared times R, and now I'm just going to solve for R. Okay, let me go ahead and do so. So it's just 167 watts divided by 4.5 squared. And the resistance here ends up being about 8.2 ohms, like so. Okay, I can't use the following expression to do this portion of the problem, by the way, because this right here is not 120 volts. This right here is the voltage across the resistor itself. The voltage across the resistor plus the voltage across the motor, that's the 120 volts. But this right here, I would need to figure out first in order to use this formula. So that's why I use this formula here directly to find the resistance in the motor. Okay, so be a little bit careful about that. I tend not to use this expression here very often in problems because the voltage V in the numerator of the expression gets to be a little bit confusing. So then therefore this V right here, if I was going to do this calculation, is the root mean square voltage across just the resistor only. Okay? Okay, so that completes that problem. Okay, go ahead and pause the video and move on to the next problem. Okay, and this is the problem associated with the hairdryer. Okay, let me go ahead and do some erasing here. Okay, now as it says in the problem, the hairdryer is just thought of as a resistor. Okay, a hairdryer does have a motor which rotates a fan and blah, blah, blah. There's a heated coil of wire, et cetera, et cetera. But let's just think of your hairdryer as a hot wire. That's good enough, okay? All right, so right here is a resistor, like so, and then once again we have right here a generator. Okay, so we do this first of all in the United States. As it says, you have your hairdryer and you plug it into an ordinary wall socket here in the United States. Okay, so VRMS is equal to 120 volts. And then we're given here that P deliver is equal to the same thing here as the P across the resistor. The reason for that, once again, is that all that we have in this circuit is the generator and the resistor itself. And that's given to us here as 1,000 watts. All right, so it says calculate the resistance in the hairdryer and also the peak current drawn. So let's first of all find the IRMS value of the current. We'll do so by doing the following. So P deliver equals IRMS times VRMS, and I'll just solve for IRMS. All right, so this is 1,000 watts and then divided by 120 volts. Okay, and that comes out to be about 8.33 amps, like so. And then this IRMS value here, this is equal to the peak divided by root 2. So let's go ahead and calculate the peak by just multiplying by root 2, like so. And the peak value here, I naught, that comes out to be about 11.8 or so. Yes, like that. Okay. Okay, and now what you do is you take your hairdryer and now you take it to Europe. Okay, so for those of you that have been to Europe, you probably have noticed that the wall sockets in Europe look different in the United States. And then if you took your devices with you to Europe, you would have to bring with you an adapter such you can then plug your devices into that new wall socket. The reason for all of this is because in Europe, the standard VRMS is different than it is in the United States. It's 120 volts in the United States, but it's 240 volts in Europe. In order to take that into account, you have to bring an adapter with you. The adapter is just an additional resistor that is placed in series with your device. Okay, the reason for that has to do with the second portion of the problem. Okay, before I get to the second portion of the problem, however, I forgot to calculate the resistance R of the hairdryer itself. We'll need that resistance because when you take it to Europe, of course, it's the same hairdryer and with the same resistance. Let me go ahead and find that value. So in order to do so, we'll do VRMS is equal to IRMS times the resistance R. So just solve for the resistance. Okay, so still in the United States, 120 volts divided by 8.33. So 120 divided by 8.33, and this comes out to be about 14.4 ohms. So now you bring this here, this hairdryer, to Europe. All right, so now we go to Europe, assuming we ever can again, that is. Okay, so now we go to Europe, where the IRMS value, or the VRMS value, excuse me, is 240 volts. Okay, and then let's say that you plug this hairdryer in without means of an adapter. Okay, watch what happens with the amount of current that is drawn. So the amount of current that's going to be drawn here, VRMS, is IRMS times R. It's the same hairdryer. So let's go ahead and solve for the IRMS here. That's VRMS divided by R. All right, so this is 240 divided by the resistance from a few minutes ago, and this is 16.66 about amps, like so. It's twice as much as the current that we draw in the United States. with the exact same hairdryer. Okay, this is not good. The reason why this is not good is because now let's go ahead and calculate the power loss through the hairdryer itself. Okay, the power loss through the hairdryer now is IRMS squared times R. So it's this guy squared and then multiplied by the same resistance. So square this and then multiply it by 14.4, and this works out to be 4,000 watts. So this is the amount of energy per second that's passing through your hairdryer, whereas when you operate it normally in the United States, it's only 1,000 watts. If you're basically drawing this much energy per second through your hairdryer, this is rather catastrophic. This value of the current here is quite high. If the value of the current here is quite high, then it's probably going to melt your wire or melt your hairdryer or catch your hairdryer on fire or something like that, which is presumably the last thing that you want to have happen. So then therefore what you do is you bring an adapter with you when you go from the United States to Europe. That adapter is an additional resistor. In other words, what it does is it increases the value of the resistance such that it brings this number down and it brings this number down. It brings it back down to 1,000 watts, for example. Okay? All right, so that completes the basic problems here associated with the kinematics then of alternating current. That completes this portion here of chapter 25. Thank you.